Okay, welcome to Chapter 15, Section 2. Let's get right to the key ideas. What are some ways to measure and compare waves? How can you calculate the speed of a wave? Why does the pitch of an ambulance siren change as the ambulance rushes past you? So, let's get right to it. What are some ways to measure and compare waves? Amplitude and wavelength are measures of distance. Period and frequency are measurements based on time. So those are kind of four things that we're going to measure: amplitude, wavelength, period, and frequency. Amplitude measures the amount of particle vibration. So amplitude is the maximum distance that the particles of a wave's medium vibrate from their rest position. For a transverse wave, that's measured from the rest position to the crest or to the trough, not from crest to trough or trough to crest. It's just from its equilibrium or rest position. There's kind of usually will be a line in the middle of it, a straight line. It's from there to either the crest or the trough. That's called the amplitude. That's measured in meters. And as you can see here, there's a rest position, this dotted line here through there. And you have the amplitude. Here it's the distance between the rest position and the crest. And in the other one here, it's the rest position to the trough. Wavelength. Wavelength is the distance between two equivalent parts of a wave. So wavelength is the distance from any point on a wave to an identical point on the next wave. For a transverse wave, it's measured from crest to crest or trough to trough, represented by the symbol lambda, and it's expressed in the SI unit meters. So you can see here on a transverse wave, it is from crest to crest, trough to trough. You could go from the middle point to the next repeating middle point, but it's generally easier to just go crest to crest or trough to trough. In a longitudinal wave here, you have it from one point in a rarefaction to the repeating point in the rarefaction, or from compression to compression point. Both of them measured in meters. Amplitude and wavelength tell you about the energy. If it has a larger amplitude, it's got more energy, and generally shorter wavelength has more energy. Period. Period is a measurement of the time it takes for a wave to pass a given point. So period in physics is the time that it takes a complete cycle or wave oscillation to occur. So this is just one complete cycle of a wave. How long does it take? If you had a stopwatch, start, stop there on one cycle, see how long it takes. Represented by that symbol capital T, expressed in SI units of seconds. In the diagram, the period of the wave is 2 seconds. So you see here a wave, crest of the wave here, to move to here, to there, back to there. It takes 2 seconds for the wave to go, basically to go down and up. It takes 2 seconds for that wave to pass. So it's here to trough, goes down, back up to the next crest. So crest to crest, it takes 2 seconds to do. Frequency is a measurement of the vibration rate. Frequency is the number of cycles or vibration per unit time, or also the number of waves produced in a given amount of time. It's basically like saying how many cycles per second is the wave oscillating at. Usually expressed in the SI units of hertz, represented by Hz, which is basically equal to 1 cycle per second. 1 hertz is 1 wave or 1 cycle every second. In the diagram we have 0.5 hertz, which means that there is half of a wave every second. So here from 0 to 1 second goes from crest to trough, and that happens in 1 second, so that's half a wave in 1 second. And then back to the crest in 2 seconds, so the time is 2 seconds. So you have a wave that happens every 2 seconds, or half of a wave every second. Alright, so let's watch this little video on characteristics of a wave.
Amplitude is the height of the wave. It is the maximum distance that the particles of a wave's medium vibrate from their rest position. Wavelength is the distance from any point on a wave to an identical point on the next wave. Period is the time it takes for a complete cycle or wave oscillation to occur. Frequency is the number of waves, cycles, or vibrations produced in a given unit of time. Wave speed is calculated by multiplying frequency by wavelength.
Okay, so we'll get a little more into wave speed here in a minute. The frequency and period of a wave are related. Frequency is the inverse of the period. So frequency is 1 divided by the period, or F is equal to 1 divided by T. So wave speed. How can you calculate the speed of a wave? The speed of a wave is equal to the wavelength divided by the period, or the frequency multiplied by the wavelength. They both give you the same thing. Wave speed equals wavelength divided by period. So speed is distance divided by time. So wave speed is the distance that the wave travels, which is its wavelength, divided by the time, which is the period. The wave speed is very similar to the regular speed equation, distance divided by time. It's a wavelength divided by period, or V is equal to lambda. It looks kind of like an upside down Y, which represents wavelength, divided by capital T, which is the period of the wave. Wave speed also can equal frequency times the wavelength. Because frequency is 1 over the period, you can take the wavelength and multiply it by frequency, which is the same thing as 1 over T, and it still gives you the same information. So wave speed can also be frequency times wavelength, or F times, that should be lambda there. Alright, so let's go for the equation for the speed of a wave.
The speed of a wave equals the product of its frequency and wavelength.
Okay, simple, short, and sweet. Velocity, speed of a wave is frequency times the wavelength. So we've got to do some math skills. Sample problem. The string of a piano that produces the note middle C vibrates with a frequency of 262 Hertz. If the sound waves produced by this string have a wavelength in air of 1.3 meters, what is the speed of the sound waves? So list the givens and unknowns. Frequency in this case is 262 Hertz. The wavelength is 1.3 meters. And we want to know what the wave speed is. So going back to the wave speed equation, we have the equation for wave speed is frequency times wavelength. We insert the known values into the equation and solve. So 262 is the frequency, 1.3 is the wavelength, so you multiply those two together and get 341 meters per second. Now, the speed of a wave depends on the medium in which it is traveling. So in general, wave speed is greatest in solids and least in gases. In a given medium, the speed of waves is constant. Kinetic theory explains differences in wave speed. Light also has infinite or finite speed, which basically means it has a set speed, and you can't exceed the speed of light. And going back to, in general, the wave speed is greatest in solids, least in gases. Speed travels very fast, like in solid materials. Metals travels very fast through metals, travels fairly slow through like air. Speed of light has a given value. It's represented by the letter C. It's not specific heat. This is for the speed of light. It is 3 times 10 to the 8th meters per second. Give you a little perspective on that in units you might understand. It is 186,000 miles per second, so it's extremely fast. So for electromagnetic waves, the speed of light is equal to the frequency of the light times the wavelength of that light, and it always has to be equal to 3 times 10 to the 8th meters per second. So if the frequency goes up, wavelength gets shorter. If the wavelength gets longer, the frequency goes down. So, something called a Doppler effect. Why does the pitch of an ambulance siren change as the ambulance rushes past you? Motion between the source of waves and the observer creates a change in the observed frequency. Pitch is determined by the frequency of the sound waves. So the pitch of a sound, how high or how low it sounds, is determined by the frequency at which sound waves strike the eardrum in your ear. A higher pitch sound is caused by sound waves of higher frequency. So in turn, a lower pitch would be because of lower frequencies. So frequency changes when the source of waves is moving. So the Doppler effect is an observed change in the frequency of a wave when the source or observer is moving. So if it's moving towards you, it's emitting sound at a certain speed, but because it's adding speed as it's moving towards you, it will increase the frequency, so it will make it sound like a higher pitch. As it moves away from you, as the object moves away from you, it's taking away speed from that sound, so it lowers the frequency of it, so it lowers the pitch, so it sounds like it is lower as it goes away from you. So the Doppler effect occurs for many types of waves, including sound waves. It also includes light waves that will happen as well. So let's watch this visual on the Doppler effect.
The Doppler effect, named for its discoverer, is the difference in frequency of a light or sound wave that an observer perceives due to the motion of the source or the observer. Here, observer A will hear a higher pitch than the ambulance driver. Observer B will hear a lower pitch than the driver does. Let's see what happens if the ambulance is sitting still. Notice that sound waves traveling from the ambulance reach the two observers with the same amount of time between each wavefront. Now watch closely as the ambulance moves away from one observer and towards the other. Observer A hears wavefronts arriving very close together in time. Wavefronts that arrive closer together have a higher frequency. Observer B hears wavefronts that are spaced far apart. Wavefronts that arrive farther apart have a lower frequency. This accounts for the higher pitch you hear when an ambulance is approaching you, and the lower pitch you hear when it is traveling